Okay, I'm going to go ahead and get started. Hopefully more people will trickle in, and I guess we also will have people watching on live stream. Appreciate everybody coming today. It's great to be back giving a talk in person, which is nice. It's been a long time. We have a great lineup of speakers today, and what I'm hoping to do first is to basically set the stage for what the speakers will be telling us about. So I'm going to be the bad news person and give you all the things that are wrong with the system, and our speakers today are going to tell you all the good news about all the things that we're doing to make things better. So the world that I live in as a physician are these two parallel worlds where we have on one side, on the left side, we have our clinical care world. This is all of the rich data that we collect in the course of taking care of patients. All of the interviews and the notes and the labs and the medications, all the things that we send out to other institutions to run tests on. That's the rich clinical data we use. And on the other side is this parallel universe of clinical trials. And you may not have thought much about this, but clinical trials data are very highly selected and curated, and they're a tiny piece of all the data that we collect in the course of taking care of a patient. But it's the clinical trials data that we use to study patients, to learn about patients, and to develop new therapies. Right now, the way that we move data from this rich clinical system into the clinical trial system is all manual. A human has to sit there and look up values and actually sometimes hand type them into the other system. It's very inefficient and error prone. So this is what a data collection form for a clinical trial might look like. It would just have checkboxes or places to fill in the blank. And this is what the clinical research assistant would fill in, compared to all the rich clinical data we get during clinical care, MRIs and CTs, lab values, medications administered, these long notes that are dictated by the residents or the fellows or the attendings. And this rich data is really funneled down into this tiny amount of data that we get for clinical research. And a lot of this is due to basic non-interoperability, or a lack of our ability to extract data, this rich data from the medical record. And I have a few slides that I want to show you, which I think illustrate the heart of the problem. Now, I'm not going to go into the reasons we have these problems or the solutions. I'm just going to give you some, I think, iconic examples of the kinds of problems we have. So when you ask for your medical records now, the most common thing that you'll be given is a DVD or a CD. Now, I don't know about you, but the number of devices I have left that can play a CD are pretty small. You know, if I have an old enough car, maybe I could play it in there. So to get a CD full of PDF files that are your medical records is really rather useless in this day and age. And yet, for the most part, this is the state of the art. Now, there's legislation and there's rules to try to make it easier for patients to get their data, but I've been on the receiving end many times of CDs and DVDs full of images and PDFs, which is supposed to constitute the medical record. This is an example from a database maintained by the NIH that is supposed to have a lot of genomic data, and this is all the ways that the term age is represented in that database. And you can tell from looking at this list that the researchers basically just got to choose whatever they wanted, however they were going to represent age. So you can imagine if you're trying to combine these data sets together, and you're going to try to combine on age, how do you have any hopes of doing that when we can't agree upon something as simple as how old somebody is? Shadow charts are endemic to medicine. And by a shadow chart, I mean that we have this rich electronic health record with all the information, but for many groups, and in this case, I'm in oncology, we keep shadow charts on all of the kids we take care of. And a shadow chart is just a paper chart that has a lot of the same information that's in the electronic health record. We keep signed consents, we keep signed treatment plans. In this case, we keep adverse events. This binder here is for one cycle of chemotherapy for a patient. So how could you possibly aggregate data when you're fighting against this type of system? Those 3 laptops there, each one is logged into a particular pharmaceutical company's clinical trials website, and you can see the usernames and passwords taped on the front there, and that is for the research nurses to enter the data for those clinical trials into that bespoke system for that particular pharmaceutical company. We still fax tons of information around. Doctors use fax machines and pagers. Those are the things that you'll still see us using from the 70s and 80s. And fax machines are still the state of the art. I can't tell you the number of times I've asked for a lab to email me lab results, and they say, no, we have to fax it, it's more secure. I say, more secure? The fax is lying on the ground where it came off the machine. How could that be more secure? There's no argument there. They can't email, it has to be faxed. This is a true story from some of the work that I did with my colleague Brian here. We were looking to get reports. These are dictated reports on CT scans. So these are typed out reports. But to get the reports were first faxed and turned into images, and they sent us the images. So we had to develop a system where we used OCR, optical character recognition, to get the data back, and then natural language processing to pull out the meaning, where we could have just gone back to that typed report in the first place. But that would have been too easy. So again, this pervasive lack of imagination around how we share data is really hampering our ability to move forward. Clinical trials. This is a couple pages from a several hundred-page clinical trial for a pediatric cancer protocol, written in Microsoft Word, no standardization. If we look at the medications used, we'll just make up abbreviations for those medications. We'll just have footnotes there at the bottom that tell us what kind of test to run. These are all generated in Word, saved as PDFs. If you're trying to build a system to automatically do these tests or automatically create the labs, how could you possibly do that when there is so much inconsistency? And this could be solved easily, technically, by having some way to build the trials in a trial builder. But people aren't thinking of that because of the lack of standardization. This is just a spreadsheet of some genomic data. Look at column 2, 1010. What do those stand for? What kind of standardization is that? Where's the data dictionary? What are they trying to get at here? This is a list of mutations in one of our data dictionaries for a type of leukemia. Look at all of the way that those mutations are written out. One spelling error, and then now you can't aggregate the data anymore. There are very few standards for these types of data. One more example. Well, you would say, well, if I want to test somebody's hemoglobin, where do I get that? In the medical record, we have like 30 different types of hemoglobin that we send out for. Which one do I pick? Which one do I send back to the clinical trial? What's the standard? Yeah, we have a standard code for these things, but which one do I pick? Will a human decide that? Will a human make the wrong decision? And then what about free text? This is the big holy grail, this unstructured data, this free text, that all these dictated notes and these long-form expressive narratives that the residents and the nurses write. We have to develop now ways to parse out the data through natural language processing and build these pipelines to get the information out. Here's an example of a dictated report for an echocardiogram, which is a heart function test. And again, somebody has to write, in this case, this echo-infer program that's supposed to pull out the information. Well, what's the alternative? The alternative is you actually have somebody record the data as granular elements, where they check off boxes, where they actually put the data in as the data, not as some dictated note you have to pull the information out. The other problem we have is this information funnel, where we lose so much of the information. If I'm running a clinical trial and I want to know the heart function for the child, I put in this ejection fraction, 70%, means that every time the heart beats, 70% of the blood shoots out of the heart. That's the function that I record. How did that number come about? Well, it came from a report which came from a video echocardiogram, which is full of this rich information. We throw all that out in a clinical trial, and we just record that ejection fraction. Why can't we save up the information? Why can't we keep that video so that 10 years later, somebody that wants to study, say, the valves of the heart, they can do that study instead of being stuck with this ejection fraction as the only indicator of the heart function for that kid? And then finally, the mapping is extremely tedious and difficult. This is a trivial example using patient sex, but not an unrealistic one, where two hospitals would use the different numbering scheme for male and female, and a third hospital might just use M and F for male and female, and might even have a third category. how do you combine the data from these hospitals together when there's no standard? What our group does is we spend a lot of time mapping to standards so that we can remove this ambiguity, but this is extremely tedious and expensive. And when you go through this mapping process, it takes a human a long time to write this code, to do this mapping. And for something as easy as sex, this might be straightforward, but what about when you're doing tumor stage? Or if you're doing cardiac function, or if you're doing a score on an Alzheimer's test? How can you possibly then standardize those things? You have to have the standards to start with. And then finally, the most important thing we're thinking about going forward is the non-clinical data. And this is something that we call the Sociom. These are all the factors that impact our health. Pollution, weather, green space. If you have a child with asthma, maybe it's really important that they live next to a highway, or maybe it's really important with somebody with high blood pressure that they live in a high crime area. How can we collect these data and standardize them when it's a wild west of how the data are collected in the first place? How can you combine weather data from Chicago with weather data from Milwaukee if they're not even collected on the same standard? So I'll leave you with this, this metaphor that I like to use. So when ATMs first came out, when cash machines first came on the scene in the 80s, you had to go to the cash machine for your bank. If you had a Chase card, you had to go to a Chase ATM. If you had a Bank of America card, you had to go to your Bank of America ATM. And if you didn't, you couldn't get cash because the banks didn't know how to talk to each other. Well, there was a financial incentive for the banks to learn how to talk to each other. And now, this is the remote ATM I could find. You can go to any ATM in the world, put your card in, and money will come out. And why is that? It's because the banks have come up with a standard for sharing information. Why did they do that? Because there was a financial incentive to do it. There was a need and there was a financial incentive, and they got their act together, and now they can figure out how to harmonize their data. We need to do the same thing in medicine and healthcare. We're back in the 80s in some ways, and you'll hear stories today from our speakers about ways that we might start to move past this process so that we can get to a point where we can combine and share data, we can develop better cures and take better care of our patients. So over the next couple hours, we're going to hear from 3 experts in the field. There'll be a short introduction for each person, and then that expert will give 30 to 40 minutes of comments, and then we'll have a bit of a Q&A afterwards. We'll have a short break, and then we'll come back and we'll seat everybody up in front and hopefully have a panel discussion. So think about your questions as the speakers are giving their remarks. We have microphones, and after the speakers go, we're going to have mics to move around if people want to ask questions. So without further ado, I'm going to ask Brian Ferner to come up, and he's going to provide some introductory remarks for our first speaker, Harold Solberg.
Thank you so much, Sam. So it is my distinct pleasure to introduce Harold Solberg. For those who aren't familiar with Harold's work, he has been a pioneer in the medical computing field for decades. One of the foci of his career has been exploring the role of formal semantics in data interoperability, with a particular specialization in clinical terminology and data binding. Harold has participated in and contributed to multiple different standards organizations, including HL7, the World Health Organization, the ISO, the Object Management Group, the International Terminology Standards Development Organization, and the World Wide Web Consortium. Mr. Solberg is a key contributor to the ISO 11179 specification that formalizes the relationship between ontologies and data. He has worked extensively with multiple organizations on linking ontology semantics with data model and data instances, including working with the National Cancer Institute, the National Library of Medicine, the Centers for Disease Control, and the Clinical Data Interchange Standards Consortium, or CDISC. Mr. Solberg has published extensively in journals and conference proceedings, with an emphasis most recently on FHIR, OMOP, the burgeoning LinkML modeling language, all within the context of projects such as the Center for Cancer Data Harmonization, the National COVID Cohort Collaboration, and many others. Mr. Solberg has worked as an assistant professor at the Johns Hopkins University School of Medicine since 2018, and before then at the Mayo Clinic. Everybody please join me in welcoming Harold Solberg.
Yeah, I think I'm all set. Okay, so, okay, the arrow there. Test 2, 3. Oh, wow. A lot more people here. This is kind of exciting. I'm going to start with an example. This is an example of what I'd argue is an IT system and a modeling system. Just out of curiosity, how many people here are familiar with the Seoul subway system? Not many there. Okay, good, because it's been a while since I've been on it, and I'm not sure I remember all of it correctly. But this is a basic task that if you show up there, sooner or later you've got to learn to use the Seoul subway system. And the first part of the task is something we're all familiar with. I'm in a hotel looking out over the city, and I use Google Maps. And I use a series of abstractions from my hotel location to convert it into a location thing where I can find the relative location and approximate distance, and these days get instructions to the subway entrance. So what happened there? I just started out, I had a perception of the world, it was where I was, and I was able to transform or map that perception onto a map. That's going to be one of the challenges, as I've got mapping onto maps. And then I was able to do a series of model transformations. I was able to transform it back into a set of instructions that allowed me to get to the subway entrance. And so I use the set of examples. I take a set of actions. I now become a processor. I've got an initial state, a final state. And this one's pretty straightforward. Just follow the existing roads till you find the subway entrance. And they give you a big old sign so you know how to get there, and down you go. Skipping how you pay for it, because that's another exercise into itself, you now have to make another transformation. You've got a map on the wall, and let's see, I guess it'll be a little later where I show the big map. This is an excerpt of just a tiny piece of the map. And it's got this interesting collection of colors and numbers. And what it's done, basically, is if I map my location onto the subway map here, which is this city, and this is the place. If I'm in the subway, it already tells me I'm at 631. If I'm not in the subway, I actually have to map either English or Korean or other text into this number. There we go. This is the whole map. This is what they're dealing with. And if you've traveled about, Chicago or Washington, D.C., for that matter, the level of complexity here is pretty large. It's a huge system. But you'll notice that it's an abstraction, and we have a lot of colors and a lot of numbers. So the first thing I have to do is determine my color, which is an identity function. I am on the brown number 6 line, and I'm stopped 631. The other bit I need to do is somehow I need to take this destination, which in this case I can't pronounce it, but Guangchon, and one way or another, using the maps, I've got to turn it into a number at all. So it's on the blue line, and it's stopped 438. I plot a path from my source to the target using that big old map I had there. And in the process of looking at it, I notice where the color changes occur. Color changes map to line changes. And from this, I extrapolate a set of instructions. One of the things I have to note is that wherever you've got junctures, you don't actually have station numbers. So what I need to do is I need to recognize, these station numbers are contiguous. And furthermore, where it's not listed, it's between 627 and 629. Must be 628. I've got another line going through it, and same thing, it has to be 428. Now, one of the problems you face in some place like Washington, D.C., is you get down there, and I'm on the red line, but what direction do I go? Well, you have to go back up to and find a map somewhere and say, that's right, Tottenham is this direction. So you actually have to go back and be able to read the text of station names and what have you. Here, because we've mapped it onto a set of integers, all I really need to know is say, am I going in an ascending direction? And then the station has some marker, I don't remember what it is, but it says this line is for ascending numbers, and the opposite side of the station is for descending numbers. And, right? And how many stops do I go on? Well, I have to figure out this little formula. It's always the one less than the numbers you subtract there, basically. But I have to go for 3 stops. Then I have to transfer to the blue line, pick the ascending direction, go for 9 stops, and at the end, I pop out and I meet whomever I'm supposed to meet. So what happened here is that we had 2 models. We had a source model of subway entrances, exits, lines, transfer ports, and all that stuff. And we had a very simplified target model. It was a undirected graph connected, a node identified by numbers. The ordering of the numbers specifies the ordering of the nodes. And we had, so that was an ordinal system, and we had a second nominal system in which we identified every station by both a color for the line, or excuse me, the vertex, that's right, every line between stations by a color and single alphanumeric character. So we did an identity map. So what's fascinating is I don't need to understand Korean or English for that matter, or all I need to understand, it's kind of a requirement for some communities. I need to understand the Arabic number system, and I need to understand how it's ordered. And I need to understand, I need to either be able to recognize color, or if I can't recognize the color, I need to understand the set of single-digit letters that covers that. But once I've figured that much out, my knowledge of how numbers go together and how identity work allows me to traverse this system without reading a word of Korean. So what's going on here is, on the abstract level, is we're doing a mapping between 2 models. We have a source state, which is state 1, and in the case I just showed you, that's my position in Korea. And we have a target state, state 2, which is the world of colors and ordinal numbers. And I have a map that tells me how to get from my source state to my target state. And then underground in the subway system, I work in terms of the target state. I mean, I can sort of keep track of where I might be relative to the surface, but mostly I'm manipulating the target state. When I get to the other side and I pop out of the subway system, I inverse the map function and I come out to source state 1. And what I've done is effectively done a function that just transforms between 2 source states. What I'm describing here is a branch of mathematics called category theory. And it's as all mathematics done to map different categories of mathematics together, but it turns out to be a dang good description of an awful lot of what we're doing when we're creating models, be they computer models, or in this case, the computation was done entirely manually. I'd argue that there's very little difference. You could do this equally well on computers. And what we're actually doing is we're starting with our position in the world, and we're just dealing with consecutive maps, continuous refinements, our perception of the world, to how we interact with keyboards and terminals, to how we interact with forms, with storage systems, with the states of electrons on semiconductors, etc. These are all the exact same sort of transformations we did a minute ago. In a sense, it's turtles all the way down, although at some point down at physics, you finally get a bottom turtle. Okay, one of the things we hit is here we publish both the source and the target state. If you go back to Korea and the Korean subway system, what's neat about it is because we understand both systems, it means that if we don't like colors for nominal features and numbers for ordinals, we can come up with our own color and ordinal system, and as long as we understand the mapping that we did there, we can compute what they're doing in a brand new way. Or if we understand the target system, the ordinals and numbers, we can add new applications to it. We can add new functions. Where's the train? Well, the train's between these 2 numbers. The other really important thing about this system is that we get a clear picture because we understand its nominal and ordinal systems and how it goes together. Could we, in fact, represent the Washington, D.C. subway system on here? And some of the questions we'd have to ask is, well, we're talking about a contiguous system. Is the D.C. subway system contiguous, or are there gaps? I'd have to go back and look, but I think this deals with one train per track. Washington, D.C. often has more than one train arriving on the same track. But we can use this mapping, we can use what we've got here to decide whether this applies to our case. Now, what happens if we hide the target model? What happens if we say, well, this is our secret, and you can enter into the subway system and you can tell us where you are, and we'll give you a set of instructions on how to get out on the other side. Or, one worse, what if the source model's implicit? What if we all know how the Korean subway system works, and so this is just a tool for people in the know to get around? What you lose is the ability for outsiders, people that understand transit but need a different system or have dealt with a different system, their ability to actually work with the system. And the other thing we've lost is the advantage to build on to this, this missing information, this hidden model underneath. When I started computing, healthcare computing, back about 1975, we had, it was called the CLIN Data Laboratory Computer System. And it accepted inputs from terminals and keyboards. It created output on printers. And we'd also talked with a couple of the early laboratory chemistry vendors and had worked out systems that they would communicate laboratory data. This was the entirety of the input and output. You could pay us a whole lot of money and we'd build you a new report. If you had a new laboratory computer, you could pay us a whole lot of money and we'd create a new interface for it. The whole thing worked, but the key is that how the system worked, the models inside the system were entirely hidden. And in fact, what's interesting is this was well before the notion of SQL or database management systems. We actually mapped the various data right down onto physical sectors on the disk. We had mathematics where you computed the sector and you knew what a patient record looked like, or we had linked lists for our blood bank data, and every so often somebody would overwrite a link by accident and then we could manually rebuild linked lists. But the internals was hidden. Eventually, other people started showing up with systems and said, you know, we'd really like to get at some of that information. We've got a computer over here that we're going to be working with the laboratory information and doing something else. So we said, well, that's great. You tell us what your model's about. We'll tell you what our model's about. We'll talk together about a format. And when we get done, we'll put something together and the two of us will program up an interface between these systems. What it amounts to is that both of the systems' mapped model was hidden. Both of the systems' source model was implicit. We had to actually get together and say, well, how are you really using this computer? What is your workflow? When is this data complete? And we built a bespoke model between them, and we loved it as a vendor because we made a lot of money. We quoted one of these between two of our systems at $100,000 because our systems were tailored to each customer. And so there were two system models, even if there was the same computer. Oddly, our customers didn't like this. And this is part of the reason this thing called HL7 Health Level 7 came into existence in the late 1980s. They said, we're tired of paying all this stuff. We need to come up with a standard to exchange data between systems. So instead of having the bespoke model in there, we want you to arrive at a common transfer model for various aspects of healthcare. And then we can, the source system can write a mapping to this common model once, and the target system can write a consumer of this common model once, and we're good to go. Now, this was in the period of the OSI 7-layer stack, which was an interesting abstraction. And in fact, what it really was a sequence of 7 layers of mapping, taking a model on each layer and defining how it transforms into the next layer down. So you start at the application layer, which is the semantics of what the dickens you're doing. You work through the various layers underneath each one, which has a different model, and each one which has a different way of doing things. And you finally get down to the physical layer at some point where you pipe it across the network, and then you just reverse those series of mappings. You come up on the other side. Layer 7 was the semantics of the whole thing. It's what we're doing and how we communicate it. And that's where the name HL7 came in, the HL7 standard. Healthcare, unfortunately, seems to have always been about 10 to 20 years ahead of the IT curve. The requirements seem to always get to be just a bit more than what's there. And what HL7 versions 1 and 2 discovered is that while it's great to talk application to application, people hadn't even agreed on wiring voltages at that point. There were different wires you connected to computers. And there were very few standards going all the way up. So HL7, fortunately, they were able to abandon most of the wiring standards before 2 came out. But they talked about how one formatted a record, how one formatted a field, what a record looked like, what a message looked like, what a session looked like. And they did all this work. So HL7 version 1 and 2 got layers 1 through 6 put together pretty well. It was the HL7 way of doing things. Unfortunately, when it came to the application layer, this was left largely to the user. You had a set of frameworks and forms, and you just had the detail of figuring out what you put into those frameworks and forms. Needless to say, we liked that as a vendor, because we could still charge a lot of money for defining how to fill out HL7 messages. But HL7 realized that's not where they're going. So they set off on version 3. Now, one of the mottos of version 3 is optional is a 4-letter word. We're going to get all these options out on how you encode your laboratory records and how your data is represented. What we're going to do is we're going to build a model of healthcare. And we're going to use this model of healthcare to then map to the messages that we have coming out there. And if you remember that one I had way earlier, on the outermost layer, there was the human being perceiving the world. And I would argue, some of the philosophers in here may agree or disagree, that the outermost mapping is an organic abstraction. Our vision, our perception, the way our brain works, is we're mapping from models of perceptions to our model of reality. And that's great. That's not something we're going to replicate anytime in the future, maybe limited senses in AI. But HL7 kind of got stuck out on that layer of the model. Arguably, they were at layer 8. They said, well, we need to take care of building a model of healthcare. And once we get that done, then the issue of mapping it's going to be easy. Well, surprise, the model of healthcare is really big. In fact, they never found the boundaries. And they kept going. They were saying, well, are we done? Well, not really. We need to model this area of medication that we haven't done before. And do we have enough detail? Well, somebody might care about more detail. And they produced a huge model that covered a small amount of the domain of healthcare. And when it came to actually getting these messages put together, they were having so much fun that they give you a set of rules. You could get books, you could get courses on how to map from their model of the world to messages, but that was left as an exercise to you. Oddly, people didn't beat their door down saying, we want to make these HL7 messages. In fact, what's impressive is that people actually did manage to make HL7 messages in that circumstance. So, it was way back 2012 or something, they finally had to throw in the towel and admit that no matter how much we model, we still haven't got transactions going on. And they came up with, it was called Fresh Start originally. We finally admitted to a community that had a lot of skin in the game, this isn't working. And a very few collection of individuals, 2 or 3, said, well, let's go back, and we've got all these wonderful rules for creating these messages. Let's just go back and specify a set of messages. We all know what we're doing. And furthermore, let's not try to solve the world. Let's just solve messages that people normally use. Let's give them an escape route, so that messages that we don't use, you can still put in as tag value pairs. And incidentally, over those 12, 15 some odd years that they'd been working away on V3, the nice thing is that all the rest of the ISO stack got redone for them. The internet that we use today is, complete with XML or JSON or whatever's the current fad. That's all there. So they no longer have to specify any of that. All they need to do is specify that FHIR resource model. And that's where we sit really on the healthcare today. Okay. Going back in time, this is 1976, Edgar Dijkstra, whom the people that had met him, apparently he was one of those people they say are well on the spectrum. But he wrote an interesting book called A Discipline of Programming. He, by the way, before he wrote The Discipline of Programming, wrote a programming language called Algol that got quite a bit of acceptance here. And he came across, he said, we've got all these wonderful programming languages, but they seem to be making things harder rather than easier. One of the things he discovered, and I still think needs to be driven home, while his examples were simply mathematical examples, he discovered that the software really, first and foremost, is for communicating to human beings. The fact that a machine can interpret what I've put in this software is interesting, but that's not what we should be using it for. We should be using it for making sure that we have modeled what human beings think they want modeled and represented in computer correctly. The other thing that he found was particularly interesting is he set out to come up with a way to program down to the last instruction how to do these interesting mathematical transformations. What he realized in the end was that non-deterministic implementations were actually a lot better. This is your source model, this is your destination model, and this is the mapping between them. You know how to manipulate things in the destination model. That's left as an exercise to you. The important thing was the two models and the maps between them. Another interesting thing he came up with that I didn't understand until I started putting these slides together is he had a very odd definition of semantics. And the notion was that if you come up with a function that transforms content of the source model to the target model, the weakest interpretation, the weakest precondition for the source model is what he called the semantics. And I thought that's an odd name for semantics. But if you really start thinking about back at the subway there, when we were dealing with the way that the subway system and the stations mapped onto colors and numbers, what we were really defining was the set of things that that target model could handle. The semantics of that set of things could be generalized to any connected graph, certainly with cycles, and a nominal system for identifying lines, collections of lines on the graph, and an ordinal system. And in fact, you could use that for all sorts of other things. A great example of a semantic model, I didn't put one in the slides here, but when the Walkman first came out, they came out with the buttons for forward, reverse, pause, stop, fast forward, fast reverse. And this controlled a magnetic tape, a cassette tape inside there, which was in an abstraction. It was a linear sequential access system with a beginning and an end. These days, that same set of icons that appeared on the Walkman will appear in situations where if you see it, you know, I'm dealing with a linear sequential access system that has a beginning and an end. And it could be sound, it could be video, it could be anything that involves that map. So that would be the argument that the semantics of that system is reflected in those sets of buttons. The other thing that Dijkstra came up with that's really important is that modeling makes programming hard. I just hated it when I first learned about modeling in the Mayo Clinic when, well, it was the precursors to UML came out. And the notion that we actually had to sit down and figure out what we were talking about before we started writing code was not fun. it was work. Coding, it's great. You put a little in, you try it out, you see whether it works, you put a little more in, and you're getting all these feedback mechanisms. Modeling is hard. Modeling is doing mathematics, and modeling is also understanding the rules of the community that you're building a system for. His little quote here that we still see it going on today, only by making it visible that can we hope to overcome design programs, right, design with a high level of confidence, rather than smearing code, producing softwares with conjectures that wait to be killed by the first counterexample. And I think a lot of software is still done that way today. I mean, they advocate for it in Agile. Go out and build something and then get the user to come tell you what you did wrong. And I'm not saying that's the wrong way to do it. In fact, there's some advantages to doing it that way, but you need to understand that what you're doing is you're building a target model and you're saying, do you guys map onto this? So some suggestions here as things I want to just, I don't know, how am I doing on time, by the way? There's no time indicator on here. Okay. First off, I think the source model, the target model, and how they map should all be there. They should be explicit. So much of the models we deal with today they're tacit. And in fact, when I work with people building models, one of the things I look for, I start asking questions. Okay, when you get the data, do you always put it in here? When this transform occurs, is it always done this way? And what I look for is people that say, come on, you're wasting our time. Everybody knows how this works. Because you know you've hit on a spot that you say, well, I understand, I'm not wasting your time. I have to tell the computer, you tell me. And you get the biggest arguments in the room where everybody that knew how it worked turns out to have an entirely different perception of what goes on. Making these models is really important because otherwise you can propagate errors clear down into systems that have been running for years. And openly available, I put to a community of interest, but I do think models need to be openly available. In fact, I'm willing to argue that models, at least the source models, are one part of this thing we call ontology. But the other part is the mapping. And that's going from the source model to the target model. And when you do the mapping, let's see, do I catch it on the next? I'll catch it again in a minute. But when you do that mapping, one of the things you have to decide is what elements in the source model are irrelevant. Do we record hair color? Do we record whether earlobes connect to the head or are dangling or not? I mentioned that one because that turns out to be an interesting data point on some types of breast cancer. But what of my source model do I actually want to record mapped to this target model? There's things that you omit. There's things that are constant, that I only deal with pediatric patients. Therefore, I don't have to state that these are children. I just know it. I deal with an OBGYN clinic, and if there's a record in my system, they're female, have a good day. It's really important to get that information down. What do we agree on? Because that's one of the places where mappings are going to fail. The next thing you're interested in is what are we going to blur? What sort of things can we abstract? And that's where coding and classification comes in. I can record all the details about somebody's appearance, or I can come up with a code that says that if I say this code, you can assume that they have all of these details. The problem with that is that it blurs things. So if I've got 6 colors of urine coming into my urinalysis system, and it only recognizes 3, then I have to decide how I map some of those things on. Once I've blurred it, I can't go the other direction. And in fact, it reminds me, when I was a kid, my mother was an early photographer, and she got me one of these enlargers. And so I could go out and take pictures, put the film in the enlarger, and then blow it up and focus it and print it. And this was a wonderful revelation for me, because I'd been having a lot of trouble getting these things in focus. And I said, I don't have to worry about that anymore because the enlarger focuses. And so I went out and took pictures paying no attention to focus, and it's embarrassing to say how long I spent on that enlarger turning the focus knob before it registered that once you've lost the focus, you can't get it back. Same here. Once you blur the information, once you aggregate it, you're never going to de-aggregate it. So be real careful about aggregation. As I said, the outermost map, that's the nature of being. That's what we do, I would argue, as human beings. That's what our dictionaries are for, our textbooks. Schools, that's one of the places where we gain a huge amount of tacit information, where we share information and we share models amongst each other. The target model, the outermost target model, is an agreed set of semantic and syntactic rules. Now, the reason I've got this strange thing here, this Helsinki Principle, is that I went back to read a reference source that I've known about for years, and it's really embarrassing. It's ISO TR 907, 1987. As with these sorts of great standards done by ISO, theoretically, you still have to pay for the thing. It's really, I mean, that's part of the reason it isn't wider used, although you can find all sorts of watermarked and other copies here. But it tells us how to do this whole model mapping thing. These guys spent a huge amount of effort on this with the technology they had. They proposed a modeling language. They proposed an ontology language. They talked about predicate logic. They just put the whole thing in here. One of the interesting things is that this was in 1987, and they'd realized we had a real semantic problem in the data modeling we were doing. So they said, well, we're thinking within the next 4 or 5 years, people are going to come up with this conceptual schema modeling facility. Should sound mighty familiar to people that were in the conversation this morning. We're still figuring that in the next 4 or 5 years, somebody's going to come up with a conceptual schema modeling facility. But it tells us how to do it. I'll skip these here. I mean, basically, universe of discourse and how you get from the conceptual schema, which is the source model, to the information base, which is the logical model. The whole notion of how they go together. And yeah, I'll stop at that. The other thing that this language talks about, it talks about sentences in your model. And you go various places, and yet on the left-hand side there, what you're looking at is this is a fragment of a FHIR patient record. This is a data record, a patient source. And it's structured data. But some of the things you're going to notice here is that, okay, I've gone ahead, it's idea's name, so I've got kind of a, well, it's an RDF-like, but it's a predicate logic-like thing on the right-hand side where I put together some of the predicates I pulled out of that. And you'll notice that the subject of the first 3 predicates is this report itself. And what's interesting is the status generated is about an artifact in this report. If I get down a little further, I discover that this is actually about a patient. I discover that the gender of the patient is male, and I discover that the report is active. You're not going to find that information in the structure. One of the things you do when you put together structured data is you assume a lot of information. In fact, active is a great example because it's an interesting question. What is this active identifier doing inside this report? Is the patient active, and what does it mean for the patient to be active? Well, that's not the subject of this particular node. The idea is that we've got structured data for communicating sentences, but one way or another, we really need to communicate sentences. Sentences leads down to a problem that Dr. Chute has wrestled with for a long time, and we have, and that's, let's see, do I get to this here? Yeah. What's a datum? Now, it's interesting, you talk to people in the science field, and for me, data as a plural is still something I learned. It's still something that rubs wrong when I hear people talk about the data they did this and they talk about it in plural. It's people that are in science, the sign that they can get away with using it as plural without even hesitating is interesting. But what's more interesting is yeah, we've got a pile of data. We got to be finding our datums, not our data, our datums. Yeah. I'd assert that all, at least technical data, poetry maybe not, it can be represented as collections of predicates, the vast majority binary predicates. And that's really where our modeling needs to go. I need to say that the entity referenced by Harold is of type person. He has a full name of a block of text. And I'm asserting a relationship between two entities, Harold and Sam. Just like this one when I was going out here. The datum plural, the Star Trek, that most popular Star Trek character, our data. Anyway. An interesting place to note this, one of the standards I worked on that kind of fell after ISO, or after the TR 9007, ISO 11179 Part 3. Well, ISO 11179 came out of the SQL community. SQL first came up with what the SQL language looked like, and then they said, well, gosh, we got to describe these SQL models, so they came up with the SQL data definition language. And then they asked the question, if we have a DDL for our SQL tables, and you've got a DDL for your SQL tables, how do we tell whether they go together? And they went off into a fascinating space where they basically linked the conceptual schema, the semantics, with the data elements in SQL, the individual row column elements in a data record here. One of the things that ISO 11179 gets dinged on in a regular basis, and in fact it got thrown out of a rather important NCI project several years ago, is the fact that it doesn't have any model of data structures in it. All it does is it talks about data elements or datum. But modeling data structures is something that's really usefully done in UML or DDL. There's a lot of tools for modeling data structures out there. And this isn't about those models. This is how we attach semantics onto the individual elements in those models. For what it's worth, there was a brilliant and huge tome written in 1986, Introduction to Knowledge-Based Systems, that is really a complete college degree's worth of work in data processing and IT. It goes from the basics of character representations to database systems as they existed in 1976, and then on to description logics, how one manipulates them, and in the end, it comes up with this, I think it's 9-part factoid. In the core of the whole thing, you'll notice there's an entity, a relation identifier, and an entity. That's what sort of exists in RDF today. There's another, which is a universe ID, and RDF has sort of been moving there. They're saying, well, we've got named graphs, we've got collections of subject, predicate, object things. And then he goes into some of the other things, the fact that we actually have to identify this set of triples because we have to say, I said the weather is warm, and Sam said the weather is warm. There's still two assertions. But we need to have it in there. Anyway, not much further here, but the fact that Richard Frost covered this in '86, and just as an interesting thing, I attempted to implement this model in the Intermountain Healthcare Next Generation Help System in the early 1990s. And ran into some real problems. We were using this brand new thing called Oracle, and Oracle was the only one that could handle the amount of data we had. And it had an access optimizer on it. And when I put in what I'll call hypernormalized data, a subject, predicate, object, an ultra simple data model, it managed to pick the worst possible access path every time. I mean, it was the de-optimizer. And we brought Oracle in and said, look at what we're trying to do and how come your de-optimizer keeps us from doing it? And they said, well, why are you trying to do that? And we had a long discussion, and they said, well, you just can't do that. I mean, that's really the model underlying our stuff. But a bunch of Oracle people went away and got involved in the RDF community. And there's reasons to believe that a chunk of what came out of the RDF community indirectly came out of this book. Anyway, information processing is really about models, a source model, a target model, and the mapping between them, the morphisms. And both the models and the mapping need to be formal and public. That, by the way, is the what. The how doesn't. As long as you can demonstrate that you've accomplished the mapping correctly, as long as you can demonstrate that you've done the transformations required, have at it. Use the best, biggest processors and the nastiest algorithms. And if you want to do value add, that's fine. But there's a lot of things available today that still need to be assembled. I mean, everything's sitting there mostly on the shelf, and we just haven't put it together. How am I on time? I can stop now if you want. Okay, he says stop now. Because this is an interesting set of references. It's not complete by any stretch of the imagination. But this is a lot of instructions and models and maps and approaches for getting stuff done that we could put together and get into a new set of systems that consists of models and maps. Let's see, is there any I want to call out in particular? We talked about that one. Chaim Kiloff did a brilliant set of models describing the fact that it's actually the relationships between things that matter, not the identity of the things themselves. Conceptual mathematics is a whole field. Borges is just a great little half paragraph on how the king tried to get a map so detailed it ended up covering the kingdom. Welty, a book called OntoClean, or a topic called OntoClean, which is really how one makes their ontologies precise. And just the last one here that was fun, I said models and maps. Why, that makes me think of an old game I played as a kid, Chutes and Ladders. I don't know how many people have met that. But the fact that you can take the Chutes and Ladders game and map it onto a directed graph, and then you can handle any Chutes and Ladder game somebody wants to put together, or you can represent Chutes and Ladders in new formats. Thank you.
How people have looked at knowledge representation over time. One of the pieces that you didn't talk about a huge amount that I'd love to get your thoughts on is a large part of knowledge representation tends to also be in things like constraints and inference. If we have a schema with information about uniqueness, this allows us to infer existence or non-existence of certain things. If you have a constraint, you might be able to actually infer additional things, right? So like a classic example from kind of formal ontologies will be something like, all Chicago residents have an address in Chicago, even though I don't know what their address is, right? So there are certain pieces that aren't just in terms of the facts, but also in terms of reasoning. Can you say a little bit about that?
Well, in two parts. First off, there's tools, and that's a recognized problem. The TR907 goes into it in great depth, and of course OWL and its related things also deal with that. But to point out that, all Chicago residents have a Chicago address. That's not a fact about the universe. That's our definition of Chicago residence. That's terribly important. That's the bit of information you need, because when you code Chicago residence in a data statement, the knowledge that, this was a necessary requirement for this person to be a Chicago resident is really important when we get it 10 years from now and the definition of Chicago resident has changed for tax purposes or what else.
Okay, thank you.
Thank you, Harold. Let's let you go. Great. Good afternoon. My name is David Sloan. I'm a professor of archaeology here in the Oriental Institute and director of the MA program in Digital Studies of Language, Culture, and History in the Division of the Humanities. I am the co-organizer with Sam Volkenboom in medicine and Malte Willer in philosophy of an interdisciplinary project entitled An Organon for the Information Age. This project has included discussions and visiting speakers on the problem of data integration and whether AI can help in harmonizing ontologies, a problem that affects all fields of study, from 21st century medicine, as we've heard, all the way to ancient archaeology. And it also raises fundamental issues in the philosophy of language and the philosophy of mind. So in that context, I am very delighted to introduce our next speaker, Zachary Ives, who is the department chair and Adani President's Distinguished Professor of Computer and Information Science at the University of Pennsylvania. Zach's research interests include data integration and sharing, managing big data, sensor networks, and data provenance and authoritativeness. He is a co-author of a textbook entitled Principles of Data Integration, an authoritative and well-written survey of this topic that I use in my own classes and have benefited from myself. Zach's current research focuses on building data science platforms using techniques at the intersection of databases, machine learning, and distributed systems. He often works with life scientists, especially in genetics and neuroscience, and is a co-founder of Blackfin Incorporated, a company focused on enabling life sciences research and discovery through data integration. We are excited to welcome Zach back to the University of Chicago. He was here 2 years ago, in October 2019, when he gave a stimulating talk under the auspices of our Organon project entitled Data Integration to Facilitate Data Science. I have very good memories from back in the mists of time BC, before COVID, of Zach's interesting ideas and his warm and engaging presence with us in person and the great conversations we had after his talk. We've been eagerly awaiting a chance to repeat the experience and to hear what Zach has learned in the past couple of years about this crucial and complex issue of data integration, data harmonization. Please join me in welcoming Zach Ives.
Thank you so much, David, for this very kind introduction, and thank you, everyone, for the opportunity to participate in, I think, what's actually quite appropriate, which is an interdisciplinary, integrative look at the topic of data integration. And of course, there's been already through the morning a lot of really interesting ideas and perspectives from different subcommunities, but also a lot of common themes. So what I'm going to try to do as a computer scientist who's probably worked on, 20, 25 different integration projects of different forms over the last decade and a half, try to give a few thoughts on where computational technologies work well and can help, where they run into their limitations, and where theory and practice don't quite converge, and a couple of building blocks that I think and I hope will help lead us toward a better future in terms of being able to integrate data. So of course, what I'm going to talk about is all work that's done jointly with my current and former students, as well as colleagues including Joost Wagenaar, Val Tannen, Brian Litton, and Greg Worrell. I want to start with actually a kind of a preface to all of this, which is, in many ways, the data integration problem does not start with data science or gathering structured data or anything. It starts with the fact that everything that we model and conceptualize is symbolic representation of our own personal human experiences, right? So in some sense, the first story, the first report of a data integration problem is the story of the Tower of Babel, right? Different people having different ways of conceptualizing and referring to the same terms. But I also want to emphasize that it's easy to kind of think that there's a canonical experience that allows us to map everything into the same framework. But really, because everything is so subjective, I think there's no real reason to believe that we will ever get there. Maybe in the abstract this exists. But things as simple as what are the primitive colors in the world, in fact, there's no consensus on that, right? So if you talk to somebody who learned Greek or Russian or a variety of other languages, in fact, they have a different notion of light blue and dark blue being different primitive colors. In English, obviously, we only have one term. Obviously, there isn't a one-to-one correspondence here, right? So as we kind of generalize from that and think about how different sub-communities, clinicians, researchers from different areas, people coming with different backgrounds, try to model data, we should also keep this in mind. There are hidden assumptions in everything that we encode. There are conventions. There is, as we talked about earlier today, an issue of semantic drift as well, but even within one time period, people often mean subtly different things by the same terms. They come with certain assumptions. And this is not even talking about some of the real problems as we start to try to do data science over real data, like are these things in the same units? Do they have the same precision? What about reliability? And today we have to think about other issues like even just looking at the data doesn't tell us whether the data was collected over a representative sample of the population. How do we address issues of learning something in a fair and equitable way if we have a biased data sample? Even if we drew that data sample from 25 sources, perhaps they're all skewed in some particular way. So we need to think about all of these things as we try to bring data together. Of course, our goal is to remove as much ambiguity as possible so that we can actually produce meaningful, generalizable results. Now, I want to briefly go over the process as we teach it kind of in my data science class, or as we try to practice it in the world, and we'll see a bit later sort of where it does and doesn't work well. Okay, so the basic process is fairly straightforward, right? We have a bunch of data that we want to put together. The first thing always has to be, you have to come up with a scope of what you're sharing the data within. You cannot do this in a universal way. It has to be with respect to a set of questions, a set of tasks, a set of basic concepts, a set of contributors. If you talk to any data science consulting company, they will tell you 80% of the work or more is in scoping, understanding, and then doing modeling of the ontology or the data warehouse we're trying to put everything in, and then figuring out how to get the data from the sources into that warehouse, right? So these are not trivial tasks. Where they have the most success, and of course there are many successes, are in areas where there's pretty good consensus on what we're trying to do, and there's pretty good standardization in the basic data types underneath things. Generally, for instance, in an enterprise with one CIO, with a bunch of infrastructure that the CIO can control, you can do pretty well. In general community science, it's very difficult. Okay, so let me drill down into what makes it hard, but also where computational techniques help. Let's start with something that we've been kind of talking about on and off, which is the notion of kind of representing everything in a common framework, in the ontology. And here I want to actually subcategorize the ontology, because when we talk about ontologies, there's an informal term, which kind of means any of these things that I'm listing on this slide. And there's the formal term, which usually implies that there's a so-called description logic underneath it. And how much of what you use here actually matters dramatically in terms of what we can computationally do. So let me try to briefly categorize the way that we generally talk about representing knowledge. So generally speaking, I think everybody kind of agrees, dating back to Aristotle, there are kind of notions of classes or concepts, and then there are specific instances or entities, and of course classes are related to classes, sometimes as a superclass and a subclass. And of course entities may belong to many classes, perhaps simultaneously. We're all in agreement about that. In fact, if you've ever done object-oriented programming, it's sort of even built into application environments that aren't even thinking necessarily about data modeling per se. But when you see them encoded in data storage, data structures, and databases, they go a bit further. So taxonomies are probably a thing that we've all dealt with. It's really the oldest representation for knowledge. If you've learned biology, you've learned some version of taxonomies, right? Kingdom, phylum, clade. You've also learned notions like, Patagotitan is an instance of Sauropoda, the clade, right? So those are pretty straightforward. The important thing in a taxonomy is essentially everything in there is given to us as hard-coded, encoded facts. Okay, so the relationships between these instances are by kind of one at a time pre-specified data. Where we can go a little bit further is as we start to think about schemas and ontologies. So a schema, in some sense, can be used to codify a taxonomy. Where it adds value is in being able to tell you things like every instance of some particular class has some properties, or perhaps more interestingly, can describe logical constraints and relationships between classes so that you can automate the reasoning about things. So as an example, we can say every customer for a company has an address, and we can also say a Chicago customer is some instance, which is a customer and has Chicago in the address. And the powerful thing here is you can codify this as an SQL query or a Python script or something else. If you're given customers and addresses, you can populate Chicago customer without somebody hand entering every single value. Right? So that's actually really powerful. But of course, you better get the constraints right. Okay? Then sort of a full formal ontology with the description logic has an even more powerful thing, which is bidirectional constraints. Here we can say things like a celebrity is an instance of a person, and a Chicago celebrity is a celebrity who has Chicago in some historical address. And now not only can I go through every celebrity where I have historical addresses and figure out that they're Chicago celebrities, but I can also be given something like Barack Obama is a Chicago celebrity, and I may not have his list of addresses, but I can still infer that there exists at least one such address in his past. And I can answer questions about that, right? So a query for all Chicago celebrities can return Barack Obama without having the specific data and the specific facts underlying it, okay? So that's kind of the power as we go down this set of categories. I should note that one does not necessarily need to use all of the power in the logical formalism, so it's perfectly fine to take an ontology standard and just encode a taxonomy, or a database and encode a taxonomy, etc. And in fact, we commonly do that. But I think it is important to sort of realize that sometimes while we're kind of at the bottom of this chart, we're really representing something that might be higher up, okay? Because there are different computational capabilities implied with each of these models. Okay, so what do you do once you've decided that you want an ontology or a taxonomy or a schema? Well, the next thing you need to do, if it's sort of a clean slate problem where you're trying to integrate things, is identify the fundamental classes and relationships. And actually, there's been kind of a change over time from a very philosophical top-down way of modeling different abstract classes until you get to the real data, to today people talk about realism-based ontologies where you really start more with the data and only create enough classes to capture what you actually see. So in some sense, maybe it's more like the evolutionary tree as we construct it today because we don't know how many missing species are in between. Okay, but again, I want to emphasize, however you do this, there's no one canonical way of ending up at the classes. Okay. Moreover, as you try to do data integration, what you find is there's always a tension in a couple of things. One is, how general do you want your global ontology to be, right? So I've been part of efforts where people try to define minimal information models that every single data source can contribute to. And I've also been part of efforts, Penn had a famous genomics unified schema, which had about 800 classes with about 50 properties each, where no one person could ultimately keep the whole thing in their head. So there's kind of trade-offs in each. If you go too far to the minimal side, it's great for bringing data together, and it's not very useful for actually doing data analysis because you've diluted all of your features. You end up with maybe identity, location, address, a few other things, but not all the features that you want for making predictive models. Okay? If you go too specific, then it turns out things are subtly different, so you don't integrate practically anything. And then you get the kind of kitchen sink version. So you have to find a middle ground here, and that's actually an art. The second thing comes back to my point about constraints. Okay? Just encoding the data is a first step. Encoding all the instances and correspondence tables and all of that stuff is really important. But if you really want to use computational tools well, you want to also add constraints both to catch invalid data and potentially to fill in missing data as you ask queries. You have to be very careful that as you add more of these constraints, you're not ruling out things that you didn't think about. So a prime example of this comes really from my data science class. It's pretty common that I will ask the students to model family trees, human family trees, right? And so one of the constraints they will put in is a person has 2 parents. Seems to make sense until you realize, but wait a minute, what about adoptive parents, surrogate parents, et cetera, right? Maybe 2 biological parents, but there's a lot more. If you codify that there's 2 parents, you rule out a lot of data, and you actually lose your ability to represent certain things. It's not at all uncommon for some of these standard ontologies to not fit the richness of people's source data, and I've seen many cases where people resort to putting all of their important data into the comments field and then having to parse it back out specifically for their applications, right? So there's a danger to overspecifying, which is a lack of flexibility, okay? But let's assume for the moment we actually get to a point where we're pretty happy with our ontology. Then there are a couple of tasks involved where computationally we can help, but we need a human in the loop. The first of these is really trying to take our existing data, our databases, our tables, our NLP extractors from text, and we try to match the concepts that exist in our data into the concepts as they exist in the ontology. And here, really the best thing is to have your human experts really look at the data and really vet everything, but that's incredibly time consuming. So what we often do is build tools to try to automate this. They will do things like look at the columns and see if there are overlapping and similar values. Look at the labels on the columns and see if they're similar. Maybe they're synonyms, maybe they have common substrings like last name to full name, okay? Perhaps we can codify through data dictionaries or through other things some kind of common knowledge about the world. At the end of the day, you often need significant domain expertise, right? So for instance, a trivial example like the one that I have on the slide, you actually do need to know something about human naming conventions to realize that full name probably corresponds to last name and first name, right? You could kind of match the substrings and say there might be a relationship, but to really understand it, you need a human, okay? We've built a lot of tools, and there are now a number of commercial products for trying to help automate this process. What happens, though, is they have a long training phase where a human expert has to give them real label data. They learn which out of these kind of value similarity, label similarity, et cetera, matters. Then they can try to automate that for other data sources, okay? There's also the corresponding side, which is called entity resolution or record linking. This is now saying, you know, I have names from 2 different databases. Now I want to figure out if these represent the same person. So if I ask you, are Smith J and John Smith the same person? I hope your answer is, I'm not sure. All of us know enough about kind of Western naming conventions to realize that, you know, the case of the letters, the order with the comma, all of that stuff can be mapped away. But we also know that Smith is a common last name and that Jay and John may or may not be the same thing, right? We may need to look at other evidence. For instance, do they have the same circle of friends? Do they have the same address? Even there, we're not 100% sure. What if it's Jay Smith and a family member, right? So we can only be mostly sure here unless we have extra data. Note that the most intelligent AI system, the most brilliant person can never tell us without having external information. Are these or are these not the same person? Okay, so we can build tools that try to look at things and rank them for confidence and threshold, and they will do pretty well as long as we acknowledge that they're going to be imperfect because the data simply does not have enough information to truly disambiguate 100%, okay? And again, there's lots of AI techniques that can be used for this. A very big component to all of this tends to be you hire a bunch of crowdsourced workers to help match some of these things to train an algorithm to do better at this, okay? So those are the tasks where actually AI tools can really help. Now let me get to the point where actually things get a little bit harder. This is figuring out how to actually do the conversion. Just because I know I have a price and a price doesn't mean they're in the same currency, right? So I have to figure out how to do the conversion. Note that something like a dollars conversion might depend on the day and even the time. What about value-added tax? What about all of these other subtexts that aren't even captured here, right? Sometimes I need external information, a client ID or a patient ID versus social security number. There's no formula to do this. There's no lookup. And sometimes my conversions are not reversible and in fact might result in kind of duplicate information. Concatenating first and last name will give us a full name, but somewhere else we might have a full name with a middle name. And taking a full name, it's not always possible to uniquely reverse it to first name and last name. So there's a transformation here. 90% of the time, this has to be done by a human. There are some automated tools that can use heuristics to extract simple things, but largely this has to be done by hand, okay? So to kind of summarize the basic building blocks computationally toward integration and how we sort of teach the theory, we come up with a target domain, a scope, we design an ontology, we map everything into the ontology, and then, you know, as my students would say, you profit, right? But this theory doesn't always work as well as possible. And to illustrate this, I'll use one of many examples that I could. This is a project that colleagues and I started actually now, I guess 11 years ago, focusing on integrating data for epilepsy. So essentially, my clinical colleagues came to me and said, you know, for a lot of reasons, we need to build better machine learning tools to recognize epileptic seizures, okay? So, you know, a patient will generally have a bunch of intracranial electrodes implanted in their brain if they're having seizures. They try to figure out where they originated, record this information, monitor it, and a doctor will come in and look at the EEG, which you can kind of see a very simple version of here, and sort of realize, oh, this looks like a seizure, okay? So it seems like this should be something that we could build machine learning tools for, right? But what was happening is, in this community, researchers would go work with their local hospital, collect 20 patients, build a machine learning algorithm and say, my algorithm is the best ever, no benchmarking, no comparison against any other methods, and very small, non-significant data sets, right? So there's an obvious opportunity to say, well, why can't we build a central warehouse of all of these things and actually bring the greatest machine learning techniques and the greatest machine learning researchers to bear on these problems, okay? So that's basically what we did. We tried to take the state of the art from what I just described and hire some programmers, build a platform. It took, you know, really about 2 years to get it even to a kind of baseline state, and then from there we tried to build off it. So that involved, you know, doing some kinds of data design. This was very clinical, so you want patient-centric data, you know, where was the epilepsy, what were the medical records, what kind of imaging, EEG, et cetera. And, you know, what I will say is this was quite a journey. In the early days, all the PIs on the project contributed. Nobody else wanted to contribute. It was very hard to get people to look at it, so you put things up, but nobody came. And it was a little questionable whether, you know, was this a worthwhile problem? What changed everything was we sponsored a contest on the Kaggle data science site which got people from all over the world interested in looking at seizure data and building the best machine learning algorithms because there was a prize, right? So this was actually incredibly successful. We went from state-of-the-art being 65% accurate to 85% accurate for, I think, a $25,000 prize. This was highlighted by Francis Collins in his blog. There were some interesting publications. And suddenly, this little boutique epilepsy in humans site was popular. And suddenly we got interest, which completely was out of scope, right? So other researchers at Penn said, we have rat data, we have dog data. Why don't we put this into your system? Why don't you just collect our data, right? Well, we had a database with constraints that assumed there were clinical records, patient identifiers, et cetera, had to have our developers spend 3 months redesigning so that you could just take the data and the little amount of animal information and put it in. New file formats. So a bunch of time to write new code. As we expanded, we got streaming data that we didn't expect. We got data from people who were doing single electrode recordings. And the funny thing there is we were annotating spikes in the data. Well, it turns out spike means a different thing to community A versus community B. So we kind of ran into all of these problems of semantic drift by scope, our original assumptions not matching the new domain, et cetera. And it was almost like restarting the project from scratch to increase its scope, okay? Now, subsequently, we talked with, through a workshop, a bunch of other researchers in other parts of this community, and actually the experiences were very, very similar. One of the biggest problems was this kind of issue that you build something, but people don't discover it for a long time unless they were part of the original effort. So getting to discovery was super hard. In fact, later the NIH built a database portal to point to databases. Now, I'm not sure, will people discover that in order to discover the other things, right? There's always this bootstrapping question. But the other part was top-down evolution of the site was actually really difficult, right? So that got us thinking, and it got me thinking about the fact that somehow we seem to be much further along in understanding about how to build very complex software systems in an agile, adaptive way than we know how to build very complex data systems. And there's no particular reason to believe a priori that, one is infinitely more tractable than the other. So if you look at software, we've had this kind of incredible revolution in terms of open source tooling, libraries, languages, toolkits, et cetera, where people are building things upon other things. Interoperability is kind of a first level principle. It doesn't take centralized NIH funding to start each of these efforts. And in fact, companies that are starting off building things on a commercial basis are then realizing it's better to contribute them into open source because interoperability is more important than intellectual property, right? So if you've used anything in the modern data science ecosystem, it's probably all open source, some of it developed by individuals, some of it developed by companies, some of it by both. And these things evolve, they expand, and they're getting better every year. And it's much easier to solve any task today than it was a decade ago. So I think the question is, can we borrow some kind of ideas out of the software industry to think about, what would modular, searchable, reusable, composable bits of data integration look like, and how do you discover them, right? So, what is the equivalent of kind of Stack Overflow and pip if you've used the Python ecosystem? Okay, so these are a couple things that my group has been working on for a while, and I want to just highlight a couple of the key ideas as we go. Of course, we're operating on limited time here. So one of the first things that we found working in systems biology and other areas, even before we did our work in neuroscience, was this challenge that coming up with one all-encompassing standard was actually incredibly difficult because not every source mapped very nicely to that common standard. And that the farther away you went semantically from one source to what you're trying to do, in other words, you're kind of stepping out of the original context, things get harder and harder. So what we proposed to do was to really think about a much more modular, I like to think of it as a kind of hubs and spokes model like a major airline does, right? Where you have a bunch of smallish data sources for a sub-community. Think of them as like your small cities. You have a small plane that easily connects them to Chicago or New York or LA or whatever, right? And that community can easily map to and, in fact, define and expand their ontology because they're all pretty similar in how they think about the world, right? You can then think about the much harder problem of mapping between two more distant communities. So now this is like your major airplane between two hubs. Of course, that will take a lot more work, but if it's so important that it helps lots of people, there will be more investment, right? And if you have a model like that, and it's composable, then in fact you can easily add new hubs and spokes and map them to the closest hub, and ideally data will be able to come from one point and get to another, just like a plane flight, okay? So the question is, of course, how to do this, and we spent a bunch of time building a system we called Orchestra, which was all about the mechanisms for doing this in an efficient way. And I'll just try to illustrate with a very brief example. So here's an example kind of based off our epilepsy data and kind of that scenario we got stuck with, which was animal data and human data just didn't look very similar, right? So what you can imagine is our original portal took human data from hospitals, maybe either it was directly matched, let's say from Penn's hospital into our clinical ontology because we designed the ontology, but maybe somebody who's also got a hospital that's a little different, there'll be some kind of code book to look up and translate the data, okay? We could create our own animal ontology off to the side, and labs can map to that. Of course, that won't have all the clinical records and so on. And it's not that hard to even have a kind of grand unified epilepsy ontology that then brings the common points together between these, okay? And labs don't necessarily need to map to any of these. They could map even to this epilepsy master ontology, if you will. Okay, and now the goal was that we could take data, kind of combine it through transformations and mappings, as we've talked about, so that it can be imported into a different format as it goes, let's say, from hospital into clinical data. More interestingly, you can even imagine that it goes through multiple hops. So in this case, we could take data from lab 1, map it to the animal ontology, then map it to the global epilepsy ontology, and some subset of that data might actually be relevant to the clinical data. So in fact, you can bring it in without really any effort because these mappings exist. Now, the level of information transfer is not symmetric in all cases, right? Because we're not going to invent clinical records for an animal, as an example. But nonetheless, we can get some amount of information transfer here, okay? The only problem with that is one that I want to stress, which is sometimes just because you know how to convert the data and just because the concepts correspond, it doesn't always mean it's semantically meaningful, right? So as an example, we might really want to say, look, we simply do not want any data in the clinical warehouse to have come from a non-human, right? So now we have to think about kind of tracking for all the data. How do we put it together in order to integrate it? In other words, we have to capture provenance. And provenance in our system is kind of an expression capturing what mappings were done over which things, as well as which tables or ontologies or concepts were combined. And you can take this provenance and use it as the basis of filtering or ranking or a variety of other things, okay? So for instance, we can just block data that originates from mapping M5 here, right? If we're on the clinical side, okay? So the key concepts here were we want to allow for these kind of local clusters that have similar context, and then we can decompose the mapping problem into the easy parts and the harder parts that might require more investment and perhaps even more data design. And the second big piece is integrating data is much more effective if you also track the provenance and make the provenance usable as a building block toward reasoning about whether that data belongs, how authoritative it is, and so on. And in fact, as a data scientist looks at the data, they might want to see the provenance and mark off the things that are not directly related to their particular question or that seem semantically distant. Okay? Let me then talk about the other key problem, which is just because we create this network of dozens of these interesting portals and people publicize their data doesn't mean that the right people will come. Okay? In fact, I would argue this might be the biggest problem right now in a lot of these data sharing efforts is you invest a ton of effort doing something and nobody adopts it. Okay? Sometimes that's because it's not useful, but in many cases it's just because they don't know about it. So our most recent work has been really focused on this problem and focused on it in a very task-driven way. The basic idea here is if you look at modern data scientists, typically they have some amount of data that comes from, let's say, local scientific or clinical sources. They also probably have some public data sets that they may be bringing in. And often they do a whole bunch of tasks to bring all the data in. And in fact, they manually do some of these data transformations and create new schemas and basically create a local version of an ontology for often one specific task. Okay? And increasingly, they're using the same tools. One of the more common ones these days is to use either something like Visual Studio Code or notebook software like Jupyter Notebook or RStudio, et cetera, as an environment. And a great thing about almost all of those is that as computer scientists and as software developers, we can actually extend them and layer in new functionality. So we have a project that's now 2 years in called Juno, which is focused on essentially incorporating AI techniques that help data scientists be better data scientists. So what does that mean? Well, perhaps if they, in a vacuum, think about how they design a schema to import the data, or even worse, in a vacuum, try to decide which characteristics they're going to capture from the original data, they might miss some things that would make their data much more valuable down the road. Wouldn't it be useful for them to see that other people with similar needs, similar tasks, similar domains actually have these 5 other fields? Okay? They may also benefit from training a machine learning algorithm, not just with the local data, but 10 other hospitals' data that they didn't even know about, right? And there are other scenarios where we might want to take the data, maybe it has an accession number, we might want to bring in the results of looking up that data elsewhere, and so on, okay? So generally, I like to think of this as what would a programming tool's functionality be that's analogous to the autocomplete on your smartphone keyboard, but instead of auto-completing sentences and words, it's auto-completing the kind of straightforward, mundane parts of data science, like designing a schema, importing, mapping, feature extraction, and so on. We learn these things by looking at other people's similar tasks in similar domains, okay? So how does this actually work? Well, basically, you could think of our Juno system as instrumenting the computational tasks that a data scientist is doing, looking at the tables representing the data they have, trying to figure out what they're doing, and that could be by asking them, and then looking for other things that might help them. So that might be more data for training a machine learning algorithm. It might be other tables that bring in extra features by joining. It might be code that does transformations or extractions. It might be cleaned versions of data. If you have enough people working over enough shared things and shared abstractions, there's a good chance that you can actually find something that's relevant and recommendable, okay? So Juno really is a search engine that takes tables extracted from a community's computational workflows, not just the original base tables, but all the intermediate results. And essentially, it looks for other tables that are similar, and also the code around those tables, and makes recommendations to the current user. So the idea is now we actually have kind of an AI in the loop that's helping us make better data decisions, which might in turn make for more standard data practices, which simplify huge parts of the data integration problem down the road, okay? Now, we've tried very hard to do this in a pluggable, extensible way. I mean, that's what computer scientists try to do. So one of the challenges that we've learned from data integration is no matter how many individual algorithms and features you build in, somebody always has a data type that requires some unique knowledge. So you have to build a system that's really a framework for plugging in those domain-specific things. So an example is, I can build something that finds similar strings, but now I might need to generalize it to match similar names, right? That's not just string edit distance. And I might also need to specialize it to do things like matching gene sequences where it's not just a simple string compare, but there are well-known measures, okay? So it needs to be extensible. I already described there are a bunch of different reasons you want to look for tables, and there are a bunch of different building blocks that have to go into deciding whether tables are related. Once you can find related tables, you can also find related code that created those related tables. So I'll describe just at a 37,000-foot level 3 of the key things we have to look at if we're trying to find additional training data, which is to say more rows to complete my table, okay? Those are looking at the fields being basically compatible, there being common and also complementary values, and also compatible provenance. So I'll just kind of illustrate these pictorially. Kind of the first question is, are the columns in my table either identical or can I find some other schema mapping between the table I'm searching from and some other table? Okay, we're going to leverage a lot of the ideas I talked about from these AI systems, so not just looking at the column names being the same, but the values overlapping, synonyms, etc. Okay? But this is one of the first pieces of evidence that I can put these tables together. A second thing is I want to see if there are both some shared values, ideally, and definitely some new values, because otherwise what's the point of bringing in a table if it only has redundant information, okay? And the third part, and this is, I think, really important to a lot of our discussions, provenance matters. So you only want to bring in data that was compiled in similar ways, and additionally, it might have more processing or alternate processing, but that also has to be similar. So as part of our ranking, we also look at whether the computations, the data acquisition, et cetera, were done in similar ways, okay? There's a ton of complex algorithmic work to scale this up so that you can actually search over hundreds of thousands, and I hope someday millions of tables. Just to sort of illustrate how much of a difference this makes, if we just took off-the-shelf methods, even a simple table search was taking 900 seconds and more. That's kind of not acceptable for a development tool. We got it down to 1.5 seconds to 5 seconds. We think we can still go further, okay? I should note, I talked about my particular project in this space. There's actually an emerging subcommunity which is doing kind of data discovery and data lakes. Actually, Raul Castro Fernandez here at UChicago also has some work in this space, and Renee Miller at Northeastern, and a variety of other groups. So if you're interested, there's actually a vibrant subcommunity in this space. Let me wrap up now. I want to say from the beginning, right? Data integration is an incredibly hard problem because there's so much unencoded context. It always works better when you have semantically similar ways of thinking about the problem. It gets harder as you try to be more expansive, which is why community-level data sharing is so hard. What I do think can lead to hope is really thinking about how to make decomposable modular units where we can iteratively refine, develop, extend, and improve things as needed. And in conjunction with that, we need better tools that help us reuse what's already out there instead of reinventing the wheel for the 59th time, okay? So that's really what I tried to give you a sketch of. I think all the stuff that I talked about, we're really excited about it, but we also acknowledge that it's still at the beginning and needs to be even better and even faster. I want to finish with 3 things that I think are really important as we move forward. One is we really actually don't understand how to build good tools for engaging with a human to do data development, right? You want to start with some stuff, the AI recommends some things to you, you respond to it, it goes back and improves things and so on, right? There's this exciting new software artifact that's trying to do something like that. It's called Copilot. I don't know if you've heard about this from GitHub. It's recommending code to you. What would the UI for this thing look like for people actually building data? The second thing is we actually have made quite a bit of progress in engineering practices for software. I don't think we've made the same level of progress in measuring the quality, generality, repurposability of data schemas and data sets. That, I think, is something that we could imagine doing. And the third thing, and I think we actually, a number of you observed this this morning, we need new ways of incentivizing and recognizing not only collection and creation of data, but all contributions that get us closer toward integrated, reusable, repurposable data sets. One of the kind of amazing things to me about data management and data science for the life sciences is that a large part of it is based on a conjecture that I think we haven't yet tested, which is that with enough micro-level experiments where we acquire data, we can put it all together, repurposing all of these data sets for things they never envisioned being used for, and get a big picture of what's going on. I'm very optimistic that this conjecture actually can be realized, but in fact, I don't know that we can say yet that we're 100% confident in that. Nonetheless, I think it's a really great aspiration. I think there are some tools that can help us. I think there are some methodologies. This is something that's going to require contributions from experts all over the place. I really hope maybe this day could be one step toward that. So thank you all for your attention, and would love to take questions if we have time.
Aside from the epilepsy example, what other types of clinical domains have you been able to delve into?
So, sorry, excuse me. So we did actually work pretty extensively with a couple of labs that were doing different parts of genetics, mostly association studies and the like. I will say, those were always collaborations where we would talk at a high level about the basic pieces, and then there was always this challenge that, you have a group of folks doing science, a group of folks doing computer science, and a couple of software engineers in between. And I think trying to do that in a long-lived thing is really a kind of a requirement. I'm not sure that most of the NIH-type funding that I've been part of has ever been long-term enough. 3 years is just enough to build a first prototype, right? So I think that, for neuroscience, I really feel, this is, I think I mentioned, right, it was like 2010. Actually, it was really 2008 when we started, right? So now we're 2021. I think I have a pretty good idea of some of the key issues there. And in fact, there's a lot of subtleties that I wasn't able to talk about, right? For instance, if you think about intracranial EEG, there's no standardization where they put the electrodes. So you have a data set with 48 electrodes, you have another data set with 48 electrodes, and people are trying to run the same machine learning algorithm over those as if they're the same, but they're not, right? So, those are the kinds of things that I can learn after 10 years, but maybe wouldn't be evident after just building the first prototype 3 years in, right? So that's, I think probably the other area that I've worked the most with folks in. I was part of a lot of the original discussions with Lee Hood's Institute for Systems Biology, and there were some interesting things that came out of that. Also, this functional model of anatomy, which came out of UW, I think wasn't part of that project. Each of those contributes a little to understanding the problem, but I would say that, the opportunities for sort of understanding the problem, trying to develop a general solution and feed it back, that's where it's been much harder. I think this neuroscience space is really the first one where I feel like we've been able to get people to adopt it on the other side.
We may have some other use cases for you.
Would love to have them.
Do we have time for another question? Yeah, anyone else have a question? I actually have a question myself, if you don't mind, just about the modular hub and spoke model, where you have, as I understand it, pairwise mappings between ontologies, and then you can kind of transitively march across for particular. So I can see how that would work with, based on your earlier breakdown of ontology versus schema versus taxonomy, I can see how that would work at the taxonomic level. But when you get a fairly complex ontology that has all kinds of complicated predications and so on, is that a different kind of problem? I mean, does the transitivity apply there in the same way as if you're really just kind of tweaking term alignments?
This is a great question, and of course my answer will have to be it depends. But generally speaking, yes, it actually applies, assuming that you have enough kind of mappings from these things, right? I mean, basically, it's kind of as if you have kind of your base data as a bunch of tables, and then you have your derived results from the ontology and its reasoning, the description, logics, inferring new classes, and those can also be mapped. Okay, let me kind of fully confess the kind of the challenge of doing these transitive mappings, right? I mean, basically, if I think about information, what I had encoded in my source, right? For it to get to the destination, it's going to have kind of the minimum amount of information along every step along the way, right? I mean, there's no other way around it. Now, our answer to that is, okay, in some sense, our goal is the opposite of sort of global top-down stuff. What we have learned is you need to get going fast, right? 3 years to get a working system is just, not a good model, right? So you want to make it easy for easy things to be done fast. And now, can we focus our effort on the hard parts, right? So maybe for certain cases, you actually will develop richer mappings, if they matter, right? But in many cases, we don't know a priori what people are going to do with the data. And in fact, I think that's been one of the biggest challenges with a lot of data sharing systems is we kind of build them in the absence of actually knowing what the real use case is going to be. I think we definitely found that with IEG is that we envisioned some set of things, like we built all these wonderful features for doing data science through the web browser on the cloud, and what people wanted to do was like just download a whole bunch of files, right? Hard to tell a priori, and these trends change over time. So I think you want to build something in a lightweight fashion and then strategically invest in the things that are going to have the highest payoff. And a lot of this really is going to come down to understanding what are some tasks that have high payoff. And along the way, you'll also learn a lot about how well your techniques are doing because you have a use case. Okay, thank you all.
Okay. Okay, I have the honor of introducing Chris Chute. So Chris is both a physician and an informatician, and became one in the era when that was not common. It is not common now, and it certainly wasn't common when Chris started out. He's the Bloomberg Distinguished Professor of Health Informatics at Johns Hopkins. He has academic appointments with the School of Medicine, School of Public Health, and the School of Nursing, and he's also the Chief Research Information Officer for the medical school. Before that, he was the founding chair of Biomedical Informatics at the Mayo Clinic in 1988, and we actually overlapped there for about 7 years in the 90s, when, to me, informatics had no meaning at all, and yet and Chris was pioneering in the field. Chris focused his career on how we represent clinical information to support analyses and inferencing. This includes fields like comparative effectiveness, decision support, best evidence discovery, translational research. But he has a deep interest in semantic consistency, harmonized information, and ontology. He's the co-lead of the N3C, the National COVID Collaborative, and he is also part of several HIT standards groups, including the ICD-11 revision. Personally, I've been able to work with Chris over the last few years on the NCI's Center for Cancer Data Harmonization, and I've immensely enjoyed his mentorship and his leadership in that group. One of Chris's claims to fame, and there are many, is his ability to articulate the gap that exists between clinical care and research, and he's devoted his career to building a translational bridge across that chasm. And while I spent my time trying to convince people to share data, Chris actually has paved the way for making it possible. So please welcome up Chris Chute. Thank you.
Thank you. That was a very kind introduction. And since I'm the last talk on a rainy Friday afternoon, I thought I'd just talk for the next 48 hours and take you within hailing distance of your Monday morning. So let me start by suggesting that we can talk about data availability, and access to data is always a big problem, but I submit that's not sufficient. It depends upon whether you want to be a data hobbyist or whether you actually want to functionally, effectively work with organized data. And the contrast is metaphorical, of course. There's, it might be kind of fun to have a pile of unique Lego pieces that you can rummage through, but it perhaps arguably is more useful if you have a parts list and some descriptions and characterizations and can pull up the Lego pieces that you want characteristically. You might say, well, who in their right mind would do the pile model? But the reality is the vast majority of NIH data collections are data piles with virtually no indexing structure, practical metadata, or anything like it. And what's further striking is that there are a lot of senior leadership at NIH who don't see why that's a problem. So I'll just move on. So keeping the Lego motif here, the whole goal in my mind of efficient use of data is that it can ultimately be harmonized. It's a non-trivial task. I'm not saying it, just add water and harmonization happens. But the trick, if there is a trick, is to pick a standard model. And in this scenario, we have the Saturn V, the most mature of the previous generation of American rockets. And we can see that we have earlier rockets for you space fans. There's the Mercury Redstone, the Mercury Atlas, and the Titan Gemini. And we can map those arguably to a more sophisticated rocket. We do that at the structural level so that we have capsules mapping with capsules and so on and so forth. And we do it at, if you will, the semantic level so that the vocabularies, the knowledge, the characterization of these things can be coordinated. And the reason why we do that at some level, and this is a slide I've been showing, by the way, for the past 30 years. I show it at every talk I ever give, whether it's relevant or not, but it seems relevant today, is that if we think about it, everything ultimately begins with the patient. And if we take information or data around this virtuous cycle of learning, this is the learning health system, more or less, so that we can make inferences and generate medical knowledge. Once we do that, of course, we get tenure and go home. We're done. But if we're really clever, we reinsert that medical knowledge into a knowledge decision support environment to iteratively and progressively improve the quality of healthcare while learning. And that this is a virtuous cycle, or samsara, if you will. And what holds it together, what makes it turn, is this notion of data harmonization and consistency. Because if the patient data is rendered in structures and terminologies and concepts that don't correspond to the knowledge, then you need a human intermediary to bridge that gap. But we want to do it in an automated way so that the whole notion of having comparable and consistent data, both at a syntactic and semantic layer, are actually imbued in our understanding of how we manage healthcare systems, data, and information. And that, of course, sadly, is a future goal. Well, there are things, this notion that there's syntactic and semantic is a bit artificial. because there's really, you can represent a lot of semantics in structure. And structure is sometimes decomposed or conflated into post-coordinated semantics. So here's an example. You can see it with the provenance on the bottom from lots of people that contributed to this fairly contrived example, but nevertheless, you get the idea. That you can decompose suspected lung cancer into a cancer problem of the lung that it's suspected. You can put them together in where you've got a suspected cancer and it's of the lung. That's probably quite contrived. But nevertheless, and then you can recompose them all. This is not a new idea, but the principle is that you can express things as fully decomposed and deconstructed concepts in detailed facets or an information model, or you can combine them into a run-on sentence, more or less, and slap a code number on that and declare that as the semantics that you're dealing with. As I said, this is not a new idea. This, again, is another 30-year-old slide that I've been showing. Scott Bloy wrote about this in what he called the Atomic Clinical Concepts back in '84. And you can take some absurd decomposition like colon cancer and say, well, we're going to deconstruct that and say it's cancer and it's of the colon. But clinically, that's meaningless. People don't think about it that way. They think about it as colon cancer. Or we can have here's an example of a run-on sentence, Duke's B2 adenosquamous cell carcinoma of the ascending colon with POL1 mutation. Generally, that doesn't run off the tongue commonly. And if we slap a code on that puppy and say, aha, we've just turned you into a semantic ontological concept, it's also a bit contrived. So the reality is you can do it either way, and we often do. But it starts to hurt the brain, because if we pre-coordinate everything that could be pre-coordinated, and I heard one of my colleagues in the talk this morning about combining every expressible concept of knowledge with every other expressible concept of knowledge, the challenges of combinatorial explosion come to mind. And these issues of what to do with continuous data. I mean, for every 10 billionth of an increment, do we have a new concept created? I probably not. Or even at a more categorical level. Do we create new pre-coordinated concepts for attribute levels of stage and grade? And at some level, if we're talking harmonization, we have to get our schema right. This goes back to Harold's talk of saying we've got a target model and we have a source model, and we want to make sure that there's a correspondence, and we want to make sure that we have, to some pragmatic degree, a shared understanding of what we're going to represent, how, before we even get into the notions of ontologic mapping and consistency. Well, we've all heard of FAIR data. It's quite the fashion phrase among at least information folk for the past few years. FAIR expanding out to be findable, accessible, interoperable, and reusable. But one of the questions that comes up is, what does it mean to be interoperable? And obviously I'm going to say, well, it means to be harmonized, because I'm a harmonization freak. I've been saying for 30 years that to make sense out of clinical data, we have to have it become comparable and consistent, and absent that, woe be we, because it is impractical to attempt analysis if you don't have concordance or convergence in any kind of practical way. Well, harmonization, again, we deconstruct it into a syntactic and semantic problem. And syntactically, we really mean, are we using the same kind of model? Are we declaring the same facets? Do we have the same sense of a structure or a grammar, if you want to think of it that way, in a linguistic analog? And that has become, particularly in healthcare, the domain of the data standards and the data model communities. And I think they're making progress. When I entered this field, early in my career, 35 plus years ago, the game was every standard that one data standard group would come up with, the competing data standard group had to come up with a competing standard. It was almost a game. The proliferation of competing, completely redundant and overlapping standards was discouraging. We're seeing less of that these days. HL7 and FHIR more or less have come out on top. Then there's this notion of semantic interoperability, obviously the meaning, and to that extent we're in the realm of ontology. But again, the boundaries between even syntactic and semantic, as I said, are fluid. But it's the domain of vocabularies, ontologies, and classification communities, where, frankly, I've played most of my life in the lower bounds. I submit that there's another sort of set of, well, they're not orthogonal, they're actually continuous, ways of thinking about data representation and rendering. And the computer scientists in the crowd will be appalled at the naivete of my discriminating it this way. They'll say, this is a meaningless description. But for those of us that do pragmatic analysis in clinical data every day, this seems to resonate with a lot of people. And we can think of, if you will, the true data source, for true is a relative term, but the most raw data source that we are likely to pragmatically get access to more or less has an object layer structure. It's the raw information in an electronic record. And electronic records are rarely relational, very rarely. They're mostly NoSQL kinds of internal structures, mumps, other kinds of paradigms. EPIC is certainly a mump system. And I think that's more or less is becoming canonical in the context of the HL7 FHIR specification, which really gives us a JSON object base with graph structures between and among the elements view of the underlying data. Part of the problem is most data analysts have a hard time getting their head around object data. How do you put that into a logistic regression? That's their goal at the end of it. How do I put that into a machine learning algorithm? So the next, if you will, layer down from that is and I call it the integration layer. And that's to take object data and render it in a relational form. Most data analysts and clinicians and people in the healthcare domain can get their head around the concept of a table of diagnosis, a table of medications, a table of laboratory values. That's very concrete. That's very pragmatic. They can understand that, and they can actually think through, what could I do with that? What kind of questions can I ask from that? What kind of hypothesis can I pose for that? And I also submit, and in our experience, this is the layer of data where harmonization makes the most practical sense, where you really want to say, okay, we're going to have a canonical schema, we're going to have a target schema, to use Harold's notion, and we're going to map stuff to that target, and it tends to be done at a relational layer. However, even with a relational structure, which is kind of the source, if you will, for practical analytic projections, you still can't stick it into a logistic regression or a machine learning algorithm. At the end of the day, you got to turn stuff into rows and columns. And the question is, from a harmonization and a pragmatic analysis perspective, where do you do that? And projecting relational data, taking a data transform and an ETL pipeline, and getting the appropriate rows of drugs and the appropriate rows of medications and the appropriate rows of demographics into a row and column structure, a TSV, a CSV, whatever, the dreaded spreadsheet, is a necessary step. And that is something that can be done dynamically. That is something that can be done on a project-specific basis so that it can then be ingested by the typical, the usual suspect analytic software, R, machine learning languages, Python, whatever it might be, in a pragmatic way. But I do want to say that in my experience, doing harmonization makes the most sense at that relational level, assuming you're dealing with heterogeneous data sources. Now, in a future world of FHIR, of course, that becomes somewhat unnecessary. But let me describe for you, a drum roll, the national COVID cohort exam, which I've spent the last year and a half of my life fussing over. And I submit it's actually the largest ensemble of clinical research data on the planet. It's put together for COVID. There are larger data sets around. I mean, the Optum data set from United is probably bigger, but they tend to be proprietary, and they're not accessible to the research community in general. We believe that we've created the largest community-developed centralized database, and it's all about COVID cases. It's a partnership with lots of people and communities. It's, if you will, I think a fairly public demonstration of big data open science in that forum, in that we're quite obsessive about making sure that people get shared attribution, people get recognition, that in a big science context, we talked this morning about, the people in the backyard who are making the ontology maps aren't always recognized for that infrastructure investment. And in this particular community, they get authorship on the manuscripts that they've directly or indirectly contributed to. That's part of the culture. It's kind of a social experiment of doing large-scale clinical science in an open, shared attribution community with a shared resource that is, at the end of the day, a limited data set in the HIPAA sense of the term, meaning it has real dates and real geocodes, so that we have to balance very carefully this notion of keeping open access to the research community with making darn sure we protect privacy and security, because it's a big fat target for data breach and potential re-identification. Well, it's not the largest data set in the world, but it's probably the largest data set of open public health EHR data. As you can see, we've got nearly 3 million COVID positive patients out of 8.6 million total patients, almost 10 billion rows of data, which, by some computer science mechanism, certainly the Higgs boson, that's toy data, I get that. But for clinical information, that's a sizable data set. That's non-genomic. This is all EHR data. So, back of the envelope, that gives you about 1,000 rows per patient of information in this data set. And then the underlying distributions of other stuff you can see. It's not a complete full coverage of the United States. It started with academic medical centers. This dashboard is public. You can go there and peruse it in your free time. What's interesting is that we have most of the CTSAs, I think 60 out of 63, give or take, who are participating. The CTSAs is what Julian Soloway mentioned this morning that he directs here at Chicago. It's this large consortium of academic medical centers working on advancing translational science in healthcare. On the right, you see the number of data transfer agreements. There have been 90 data transfer agreements signed, meaning 90 different organizations have agreed to send us data, which is not too shabby, 66 of which have actually done so. The data use agreements on the top are basically the number of projects that have been proposed, the number of organizations that have asked to use the data. Notice there's not a correspondence. You don't have to contribute data to get to be able to use the data. So we have actually community colleges with computer science programs that are participating in analysis of this data in a credentialed and responsible way. We have 3,200 investigators looking at this data, many of which are doing so on a daily basis. So we think it's been relatively successful. If you go to the dashboard page, you'll also see the dynamic output of our publications. The publications obviously were a trickle in the beginning, but we're in the 30 to 40 club right now, which isn't bad for a resource that's only existed for 18 months and started hitting the ground at 0. 31 domain teams. What's culturally interesting about this phenomena and process has been the emergence of self-organizing investigative communities that really focus on their domain, the cardiovascular disease, renal disease, social determinants of health. And that they're completely self-organizing. The N3C community did not impose saying, you will become the cardiovascular group. They emerged among our 3,200 investigators. And again, it's this premise of large-scale science. We'd rather have 4 or 5 really good manuscripts on renal impact of COVID than 1,000 kind of quick and dirty perhaps incomplete and not as precise or comprehensive manuscripts in the same topic. So we've fostered this idea of collaboration, of multidisciplinary science that's intrinsic to the domain teams. They include data scientists, they include computer scientists, they include biostatisticians, they include obviously clinicians, informaticians, ontologists. They are genuinely a multidisciplinary, and by nature of the sociology of this program, a multi-institutional set of programs. The vast majority of manuscripts that are coming out are authored by people across multiple organizations. It's not as though the dreaded University of Chicago chose to focus on a single topic and run with it. Actually, I happen to know Chicago investigators are involved in a myriad of applications as partners with other domain teams and projects. So it's, as I said, it's as much an experiment in large-scale social science as it is in an experiment of large-scale data harmonization. So simplistically, it's not rocket science. What we did was take data sets from contributing organizations, merge them, a miracle occurs, and generate a harmonized, integrated set of EHR data that is now, as I said, 10 billion rows and growing. We're growing at about 1% to 2% per week, basically. So we take version data and combine it. It's done in a highly secure, FedRAMP certified GovCloud environment on a data enclave. And an enclave is a term of art. I didn't know it, frankly, before this, but at least the NLM, the National Library of Medicine definition for enclave, asserts that you can put the data in, but you can't get it out. You cannot download the data. You can analyze it in situ. We bring a lot of common analytic machinery, and you can bring your own Python programs. You can bring your code to the data, but you can't take the data out. That is a fundamental principle.
Find out. Testing, 1, 2. Okay. Apologies for that.
Thank you. I thought Sam was making an editorial statement and just cutting off my mic here, but in any event, so the governance around this data is very important, and the point of this slide is not to go through every twist and turn, but to say that there are many layers of IRB. Actually, Johns Hopkins is the central IRB for this particular project. I happen to be PI of that IRB. There's also an NIH IRB. There are data access committees, which are federal. There's communities of shared governance specification. And we have 3 layers of data instantiation in the enclave. We have the full limited data set in the context of HIPAA, which means they're real dates and real geocodes. We have the de-identified data, which do date shifting. It's not strictly speaking safe harbor, because safe harbor doesn't recognize date shifting, but most other IRBs do. We call that de-identified truncation of the geocode. And then, of course, we're experimenting with synthetic data, which I could go on at great length about, but the short version is it didn't work so well. So there are many, many layers of review and approval, gateways, if you will, that, again, are consistent with our moral obligation to protect this data effectively. Well, I mean, we cheated in terms of where we started. We did not start with a blank sheet of paper. It turns out there are a large number of, well, four actually, four common data models, and I always thought it somewhat ludicrous that common data models would be plural. I mean, you're hung up, Harold, on ontologies being plural. I'm hung up on common data models being plural. But anyhow, so you can see Odyssey, Picorinet, ACT, and Trinetics were the four that we started with. Most academic medical centers use one or more of these models. Hopkins, being Hopkins, uses all four. And the point was there was already a lot of preliminary work on data harmonization and integration that we leveraged. So we started with the amount of information that was the warehouses that already existed in these. Remember, we had to come up to speed from zero to basically several million patients in a matter of a few months. And we thought the most pragmatic way of doing that. We actually put this whole puppy together. We started in April of 2019, no, 20, whatever the year was. Was it 2020? Might have been. And we opened our doors for the first users in September. So we were pretty proud of that in terms of what we did. We had, as you might imagine, a fairly elaborate data ingestion and harmonization pipeline. And what was important here is to integrate the data across these four common data models and other data models in FHIR and Future. And our target data model was OMOP, just for the record, the Odyssey OMOP was our target. To ingest them, it turns out we had to manually curate all the syntactic and semantic mappings that were implicit in this pipeline. And that turned out to be over 2 million data mapping fields that were humanly curated. So, you know, you're not going to do that on a production pipeline. So we had to go from this very detailed, humanly curated process, and again, this all happened in a matter of a few months, to having an infrastructure and production at scale. And the truth of it is, to be said in this room and not to be repeated, we built that darn transformation pipeline 3 different times. We did it first as raw SQL. We did it again using an analysis tool called Adeptia. Didn't work so well. And we did it a third time in the native Palantir environment, which is essentially an Apache Spark environment that was vastly more efficient. And that's what we're using for our industrial scale operation, so that we can actually, we're getting new payloads of data from contributing sites every week across 65 plus sites. That turns out to be a lot of transformation, at least by our little standards, of doing essentially 10 billion row transforms each week. So there is a central processing activity in this pipeline that, again, 2 million structures terms are mapped. We leveraged, obviously, pre-existing work, but we humanly validated all of it. And it parallels a lot of the work done in the cancer community that SAM and those abbreviations are really the Cancer Research Data Commons harmonized in the at the NCI. We were then able to take that whole process and automate it at scale using high throughput harmonization pipelines. The pipelines themselves had to have complete transparency and clear provenance at each transformation layer with a lot of versioning, upgrades of pipelines. The pipelines are really dynamic. We keep tweaking them constantly as we recognize idiosyncrasies and opportunities for enhanced data quality. We do rigorous and complete automated data quality checks at each layer of the transform, and obviously sought to have scalability of the underlying compute resources. So of the 60 plus sites that are in the pipeline now, there are 100 transform stages. There are actually 2 million transformation, but there are 100 plus transform stages. The provenance has about 5,000 components, and that enables the pipeline developers, which are us, to quickly identify the root cause of data quality problems that emerge in use. And as you might imagine, in a data set this large, frequently, the data quality problems are discovered when the investigators actually try to use the darn data and find inconsistencies. That's the ultimate data quality metric. But we can refresh a pipeline and rerun an analysis and rerun basically the whole enchilada in under 20 minutes. Obviously, our data transform pipelines are versioned and managed from a central control area that is updated for each common data model, and we're carefully controlled and tested. And each site, each contributing site, now 66, I believe, really has its own pipeline and its own healthcare data checks. While obviously we have, template pipelines to start from, to go from a given, say, PecorNet to OMOP, the reality is you've seen one PecorNet site, you've seen one PecorNet site. There are, much to the clamor of each of these common data model communities, profound variation and heterogeneity, even in a single common data model. And that's what we discovered. In fact, one of the underlying, I should have made an emphasis of this, but we recently published a paper. Emily Pfaff was the first author at North Carolina. I was a senior author, and I more or less designed most of the effort. But we actually demonstrated that there's profound synergy in having decentralized federated data where the local data curation and provenance and the local knowledge about the data idiosyncrasies can contribute to data quality at that local site, counterbalanced with and complemented by centralized data that can do statistical benchmarking, distributional analysis, comparison at scale across every variable. That's possible in a federated environment, but darn hard. And it becomes trivial in a centralized data environment to do this comprehensive benchmarking, which is what you're seeing here in this space where we do the deployment and run that information. So we have a lot of emphasis on data quality checks, a white glove support service for each of the contributing sites. We actually have personnel that interact with each of the sites to iterate. I mean, no site, not a single site, contributed data and had it pass our data quality checks on first run. Just didn't happen for anybody, including, I'm sad to say, Johns Hopkins, that we had multiple iterative efforts before we were even allowed to have our data incorporated into the final release sets as a function of the data quality portals moving on. The harmonization effort really looks at a vast majority of quality metrics, several thousand actually, that are computed for each site, and to determine whether there's, the distributional issues come in a reasonable way. Now, this is an interesting example because this is actually the distribution for a handful of sites. The sites are columns of the data that they had for COVID test results. Obviously, in a COVID database, COVID test results are kind of a central concept, and you want them to be aligned. So we have a very elaborate mechanism of concept set generation, value set generation, equivalence generation, and we try to curate and publish those. And those too are dynamic. But you can see, negative and not detected, I mean, are they the same thing? No matching concept, well, we'll forget that. But positive, and so on. I mean, those are clearly should be the same terms, but they have different codes from different sites. None detected, not detected, variations on not detected. Again, these are the kinds of things that were integrated in our value set concept set so that we could have, for analytic purposes, ready to roll libraries of integrated value sets and concepts that can and are being used by the research community. So this is not left as an exercise to each and every domain group. That, I think, is the key point as we move forward. Well, there's another advantage to centralized data in that we're able to do a fair amount of what I call data rescue. I'm going to focus on units of measure because it's a very concrete concept. Any measure can come in, we can talk about SI units, we can talk about other kinds of units, but the units of measure used in different communities can vary. And obviously for harmonized data, you want things scaled and reoriented to common units of measure. It turns out to be fairly complex when you're dealing with milligrams and moles, because then you have to account for atomic weights and so on and so forth, molecular weights. But in general, this is a very trivial example of the same kind of concept. So here we've got sites that provide their data in pounds, ounces, and grams. You might say, why would anybody do ounces and grams? I'll defer to our pediatrician in the room, Sam, to say that it turns out kids are sometimes measured in grams, particularly when they're born. And that we suffice it to say, that's the way the data is. And the common data models do not require specification or harmonization. They are kind of loose in that respect. They assume a lot of harmonization would be done post hoc by the analyst, and we tried to do it at scale for the community one time for many use cases, not every single use case, but this is a good one. So we've got pounds, ounces, and grams. You can see the distributions. But when we got this black thing in there with no matching concept, I think there's an animation that actually points an arrow at it. So there was no unit of measure reported. Sigh. This is the data completeness problem, which we see all the time in data harmonization, where the data is sadly incomplete on things that you think they'd mention. So they give you the number. They actually report a result, but they do not have a commensurate unit of measure reported. Well, to make a long story short, it's actually possible doing central benchmarking to render a homogenized level on a single unit of measure and put them onto a common value. I think this was actually kilograms at the end of the day. Where there's no matching concept, you can infer from the underlying distribution of the data what the unit of measure was, and actually measure or recover information that would otherwise be lost. You say, well, okay, weight, that's kind of interesting, but it's a little banal, isn't it? Well, it turns out weight is actually quite central to a lot of analysis that we do, because everybody wants body mass index. Body mass, which is basically a measure of obesity. I will not disclose my body mass index, thank you very much. But it's quite central to a lot of analysis and interpretation and adjustment that we do, particularly for mortality, and turns out to be quite a risk factor for COVID. Those people with higher body mass indices are at higher risk for adverse outcomes, and that is something that we needed to adjust for commonly. Well, you might say, well, that's fun. You did it for weight. Well, the point here is that we have in blue I will leave it as an exercise for you to read that with a telescope. So we've got pH, BMI, D-dimer, BUN creatinine, respiratory, mean arterial pressure, AST, ALT, NT-pro. There's a lot of variables here, some of them having significant clinical significance that were reported without units of measure. And what is in blue are the proportion, the percentage of data that we were able to rescue by inferring a unit of measure. I mean, look at pH. You might say, well, that's kind of stupid because the unit is obvious. But if you want to be complete and comprehensive, it turns out that we have units not plausible. There's a big black space in that pH, so we want to be clear about what is interpretable and what is not. And the blue is all the data, and each row is a variable, the percentage of the data for that particular variable that we were able to rescue by inferring units of measure. I simply use that as an example where in our harmonization efforts of bringing together different common data models and doing centralized data quality enhancement and review, we were able to methodically rescue and recover a lot of data. This is an example where we report to the sites for their interest. Each column in this particular diagram is a site within a common data model. We actually partitioned this within common data models because to compare PCORnet sites to ACT sites was not a useful exercise for lots of reasons, or any other permutation of common data model sites. But you can see that what we're showing here is a typical heat map kind of problem where, in this case, it's the missingness of the information, that one site has a relatively high rate of missing information for FiO2, but it's in good company because lots of sites in general, tend to be missing information for FiO2. This is a site that was particularly, had more complete body mass index than most other sites. This site had more complete arterial oxygen sat than most other sites, and so on. But it's kind of a fingerprint so that a given site or organization can see how their data completeness, and this is mostly data completeness in this particular instance, measures up relative to their peers that contributed information in the same data model. And again, it's an effort, it's a prod to improve the data quality and completeness. They might say, wow, we didn't know we were missing so much FiO2 data. Let's see if we can get that into our data model so that we're not red in the next data quality report that comes back. This is the percent of invalid COVID-19 test results. And the point, this is frequency over data releases. This is, you can see over the first 25 data releases. The point of this slide is that using this feedback and iterative method, we were able to demonstrate to sites that, you know what, you're kind of an outlier here, and you need to get this fixed. And it's for a given site. So for this site that had 100% missing or invalid COVID test results here, you can see that by release 4 of the data, roughly 4, they were down to 0. Through this iterative reporting and information, they corrected that. And you can see most other sites came into line pretty quickly. I mean, this took, the first 13 or so data releases before they were in sight. And, not everybody's perfect. Here's the cloud of information, as you can see here, where there's still residual missing information, but, they're within a range of information that's expected. And part of the reason why the later sites tended to increase is because we were dealing with a proliferation of different testing modalities that were introduced in the latter part of the pandemic. Here's the percentage of sites where inpatient visits were out of whack, that the inpatient visits were decreasing, were lower than they should have been, and the sites on the right side where the percent of inpatient visits were brought to increase in a significant way and closer to the community norm. Sometimes these outliers are just a functional characteristic of the organization. I mean, there are hospitals that do mostly surgery and have a very tiny outpatient practice. They're going to look very different from sites that have primarily an outpatient practice. So there are some normal outliers, if you can imagine such a term, where their reason for being an outlier is not unreasonable. So that was a very quick 48 hours. I do want to demonstrate, though, this was our first publication that we submitted, and you get a sense for our commitment to attribution. We did distinguish and do distinguish between masthead authors and consortium authors. The masthead authors are on the top and the consortium authors are listed below. But we have convinced most journals that we do conform to the International Council of Medical Journal Editors criteria, even though it's a darn long list. And our point is, it was a darn lot of work, and that it took a village, literally. And we want to make sure that that village gets credit and attribution in our efforts. So thank you, not just to you, but frankly, to this community that made this possible. Melissa and I lead the effort, more or less, but we would be completely unable to have achieved a fraction of what we've achieved without the dedication of hundreds, and I mean literally hundreds. And this community is growing. As you saw, we now have 3,200 investigators, and that they are being productive with what we think is a paradigm shift. Our aspiration, quite frankly, is that this can be a future for scalable, open clinical data science into the future, where we demonstrate two things. One, that we can do harmonization at this scale, and most importantly, that the sky does not fall. One of the big reasons that we've had trouble with people contributing data is fear, is paranoia. We were fortunate in a perverse kind of way that COVID was a special case where they were willing to, go with it and grant this unique and unusual collaborative demonstration. But we're hoping on the basis of this, and that's why in the title I call it a demonstration. On the basis of this demonstration, we can convince CTSAs and other organizations to pool clinical data at a highly granular and interoperable level so that genuine team science can occur with minimal impediment, that we don't leave most of this exercise, most of this effort as an exercise to each and every investigator, but we can demonstrate and show that this can and should be done routinely going forward in large-scale clinical data research. So with that, I'll take questions.
To that last point,
Sam?
a lot of us are wondering what concessions have been made during COVID, whether it's virtual visits and CMS changes to Medicare that just allowed these things to happen. You're very optimistic that going forward we'll be able to plow ahead with these innovations, but don't you think there's going to be some slippage, and how can we push back against that?
Well, there can, and if I'm to be frank, there probably should be some slippage. What I envision and what we're proposing to NIH, and we submitted a formal proposal, although it was ranked 4th out of 14, and they're only going to fund the first 2. So we're going to have to find another pathway to do this. But we've built the darn machinery. What we have not fully done, and I was speaking with Julian Soloway about this not too long ago, is had inclusive governance at the level of each and every data study. So far, if people apply to use the resource, while we have shared governance in terms of setting the rules, setting the rules of the road, and mores and expectations and publication policies, I mean, all these kinds of things have been very shared governance, and Julian's actually participated significantly in much of that. We haven't given each contributing site a voice over whether they want their data included on a specific protocol. And that's because it got complicated. But I think if we do propose to generalize this resource, and we will, I mean, why should it be just COVID? Why shouldn't it be all the CTSA data? Why shouldn't it be data from many other sites? Why can't we study rare diseases? Why can't we study chronic diseases at a highly granular, subphenotype level? But sites may have complex reasons for wanting to participate or not. And the paradigm that we're actually proposing is to say, look, if you want to play, there are 2 things you have to agree to. You have to agree to contribute your data and allow that data to be used for centralized harmonization and data quality processes. No questions, no specific permission, no case-by-case stuff. That's the general rule. And you have to agree to review proposals from sites that want to use the aggregated data for a specific purpose, so that an investigator community would get a projection of, I don't know, a certain kind of cystic fibrosis study subset and controls. So you would have to agree to have your data contributed to that pool for that study. Sites, and that's the PCORNet model, actually. PCORNet allows sites to, is that true, Brian? PCORNet allows, I believe, sites to decide whether they want to play in a given project analysis or not. So it's a more granular governance model that I think is not inappropriate, at least as a starting point. And the aspiration is, and Julian has already said, well, I'd want to give blanket agreement to participate in everything. I think it's our obligation. And I think Hopkins might take the general principle as well. But some sites are very skittish about wanting to give blanket approval. And, it's, again, an acculturation process. People are at different phases along their confidence in team science and large-scale science, or even their belief that any of this darn nonsense is necessary.
But everything you're describing requires administration and cost and sustainability.
True. And that's why we're exploring with NCAT's alternative models to achieve what we want to do. But the main engineering has been done. A lot of the cost will be on administrative data governance and distribution. Frankly, that's negligible in the, what is it, a few $100,000 a year? It costs $25 million to build the N3C. And we want to leverage that investment moving forward.
Are there other questions for Chris or Harold or Zach from the audience? Any other comments or questions?
We're going to forego the panel discussion in lieu of just some brief Q&A now, and then we may recess early.
This will be the end of the afternoon with Q&A. We have coffee in the lobby in a few moments, so we can mingle and chat as long as you want. There are restrooms downstairs, coffee in the lobby. After this, I should take the opportunity now to thank the Neubauer Collegium for Culture and Society and its staff, including Mark Sorkin, who's there, and Jessica Musselwhite and Jennifer Hellman and others at the Neubauer Collegium for several years of wonderful support and coordination and organization of events such as this. So thank you very much to you. And I want to thank also my colleague Sam in medicine and Malta in philosophy and friends in computer science and in every other field. This is very stimulating to look at sort of a common set of fundamental issues and computational challenges from the point of view of so many different areas of research. And I've learned a lot about sort of the granular aspects from Chris and Harold too of the healthcare system, which as a, shall we say, a patient maybe I have encountered, but never from your side of the fence, and how complex it is and how much there is a lot of these human factors and governance issues as well. So any parting comments from anyone else? If not, then let's just join together in thanking our speakers and visitors to Chicago. Thank you. So feel free to get some coffee and hang around and chat for a little while now too.